Hello, everyone. I hope you're all healthy and well. Welcome to the next talk in our Golden Webinars in Astrophysics series. Our speaker today is Carlo Rovelli, who is professor of theoretical physics and director of the quantum gravity group at the Centre Physique Théorique at Marseille University. My name is Thomas Puzia, and together with Paola Donco, we have organized today's webinar for you. As in previous webinars, simultaneous language interpretation will be provided by Mr. Patricio González, who will be simultaneously translating for us into Spanish. En sus dispositivos, pueden escuchar la interpretación al español de la conferencia al pinchar el botón de interpretación que se encuentra en la parte inferior derecha de la ventana de la aplicación Zoom y seleccionar Español. We would like to acknowledge the generous support of the Center for Astrophysics and Related Technologies, also known as CATA, for its Spanish acronym, for making this series possible.
Thank you so much for all your feedback and comments. If you are watching a recording of this talk on YouTube, please leave your comments below. If you would like to support the Golden Webinar series or give us feedback, please send us an email. If you have any questions during the talk, please type them in the Q&A window. You can also upvote questions and comments on them, and then we will select the best questions for the discussion after the talk. So before we begin, I would like to briefly introduce our other panel members that are with us today. So of course, we have our speaker, who is Carlo Rovelli, Patricio as our interpreter as usual, and Thomas and I as co-hosts. From the faculty at the Institute of Astrophysics at PUC, today we have Max Bañados, who is the Dean of the Faculty of Physics, and from the Institute of Astrophysics at PUC, our postdoc Elizabeth Arthur de la Villemois. We also have the great pleasure to welcome our guest panelists today, Reza Amir Arhomand, who is the Vice President of Orange County Astronomers, Marek Demianski, who is Professor of Physics at the Institute for Theoretical Physics in Warsaw University in Poland, Paul Honingen-Heu, who is a Professor of Philosophy in the Institute of Philosophy at the Leibniz University in Hanover, Germany, and also lecturer at the Department of Economics at the University of Zurich. And finally, Adriano Fontana, who is the president of the Large Binocular Telescope Observatory Corporation, head of the Italian National Institute for Astrophysics Division for Optical Infrared Astronomy at the Observatorio Astronomico de Roma. And last but not least, of course, we have our excellent Q&A manager, Ricardo Acevedo.
So it is our great pleasure to introduce Carlo Rovelli as our Golden Webinar speaker today. Carlo obtained his PhD in physics in 1986 at the University of Padua in Italy. After that, he had postdoctoral fellowships at the Yale University and then postdoctoral positions at the University of Rome and also in Trieste. He then moved to the University of Pittsburgh in the US in 1990, where he first became an assistant professor, then associate professor, and finally full professor in 1999. He was director of research at the Centre de Physique Théorique between 1998 and 1999, and in 2000, he finally moved to France to become professor first class and then exceptional class professor of physics at the Université de la Méditerranée. Carlo has been awarded numerous prizes and honors, such as the Xanthopoulos Award, a Triennial International Prize in Relativity in 1995, and the Doctor Honoris Causa title from the Universidad de San Martín in Buenos Aires, Argentina in 2016. He's also known as an excellent science popularizer, capable of easily communicating the most complex and modern physics concepts to the public.
Carlo has published technical and several popular science books. One of them is 7 Brief Lessons of Physics, published in Italy in 2014, that has become an international bestseller with translation into 41 languages and has more than 1 million copies sold. His main research is in the field of quantum gravity, where he is known worldwide for being among the founders of the loop quantum gravity theory, which aims to merge quantum mechanics and general relativity. Throughout his career, Carlo has also worked in the history and philosophy of science. He currently collaborates with several Italian newspapers, in particular cultural supplements. And in 2019, he has been included in the Foreign Policy magazine in the list of the 100 most influential global thinkers. So we now hand over to Carlo, who will tell us about the nature and evolution of black holes, implications and observational tests from loop quantum gravity. So Carlo, please, if you want to share your your screen.
Unmute. Thank you very much. Gracias, Paula. Hola, everybody. Buenos días. Yo hablo español, entiendo un poquito, but it's better that I speak English because this is basically my Spanish. But thank you very much for this invitation. I'm very pleased and very honored for this wonderful panel and for all of you listening. I wish I could be there. I love Chile. I was in the north. I love the north, the Atacama Desert. I think I've been going there. It's one of the most spectacular parts of the planet, I believe. Breathtaking views. And of course, it's one of the places from which we look at the world because they're the best observatories in the planet. I'm going to talk about black holes and the relevance of black holes for the research in quantum gravity. In the title, there is loop quantum gravity and there is observation. I wish there could be much more about observation. There are going to be very little about observation, but some hints. In fact, only at the end, I will mention some possibility because, of course, we do have observations of black holes, but nothing for the moment that we could understand clearly it relates to quantum gravity. But I want to present some of the ideas that I'm enthusiastic about right now and on which I'm working right now. So I'll start by sort of talking about black holes, trying to make clear what do we know about them and where we are, because it has been spectacular black hole physics in the last years, in the very last years, and where I think we could go ahead from there. So let me share my screen. Okay, yeah, so this is the short version of my title. And you see, it's not just black holes. I'm going to talk about white holes. And I assume that you might have heard black holes quite a lot recently, but not much about white holes. And I could have titled my talk "White Holes." It's a lot about, it turns about the idea of white holes and what's the relevance for them. And what I'm going to do, it's listed here. First of all, I'll try to say what a black hole is. And many of you, of course, know well what a black hole is. In the panel, there are super experts who know what a black hole is better than me. But I want to stress that it's a tricky question. And I will say why it's a tricky question. What do we mean exactly by black hole, which could mislead us. And then I'll describe a black hole from the perspective which I think it's relevant. I will not use much equations. In fact, I will not use equations, but I will try to zoom on the key conceptual point which is relevant to understand what is a black hole and how this may be relevant for understanding its quantum properties. I explain what is a white hole, which is something we theoretically understand well, and in which sense black hole and white hole may talk to one another. And this part is theoretical. It's think that we know well, and is observation that we understand well. And then there will be a main jump talking about quantum effects, and that's where the speculation and the attempt to understand more comes in. I'll talk about the Hawking evaluation, and then I'll talk about the quantum regions, the quantum gravitational effect on black holes. And then the key point will be the black to white hole transition. I'll probably not go more ahead of that. So first, what is a black hole? And I think if you look in the books, there are many definitions of black holes, which might all be wrong in some subtle sense. We have some specific solutions of Einstein equations, like the Kerr solution of the Schwarzschild solution, but it's not obvious that they describe exactly the objects that are in the sky. They are relevant for that, of course. And we have some general solution, like the existence of event horizons. But it might be that once you fold quantum mechanics in, there aren't really event horizons in the sky. So I think that the best definition of what's a black hole today is just black holes are those things we see in the sky. And we see definitely a huge amount of evidence that the sky is actually full of these objects, which are the ones we call black holes, which are astonishing objects. That's a well-known picture that was obtained very recently, a year ago, a couple of years ago, from the Event Horizon Telescope, this sort of collection of telescopes all over the world, which Chile plays a major role, in fact, it's an image of a single black hole. It's the only one we have seen so clearly so far, which is 7 billion times the mass of the sun. And, you know, if you just digest that, it's 7 billion suns. Imagine 7 billions. So 1,000 times 1,000 times 1,000 suns compressed in a very small region. The actual black hole is in the dark spot at the center of this ring here. Then there are much smaller black holes. We have a lot of evidence of these things. Now, how do we know what this is a black hole? Well, first of all, it's a very funny thing to see in the sky. But if we take the theory, Einstein theory, general relativity, and we make some calculation of what would we see if a black hole, if we could see a black hole because of the light around it, the result is the image on the left on this slide here. So we would see a ring, it's called a photon ring, which is due to the fact essentially that light can turn around the black hole. So if you have any sources of light somewhere, we can see it directly, or we can see the light going around the black hole, turning a little bit and coming to us, or going to near the black hole, making a few turns and coming to us. So from this spot, we see all the light that come from all this region of the sky. And from this spot, can see all the light that come from this region of the sky. So this ring is concentrated, the light that come from all over around the black hole. So this is this ring. And this is well understood from the equations, from the geometry of the black hole, which is predicted by Einstein theory. And that's what is expected. And if of course, if you make a picture that not well focused, you get that. And that's exactly what was seen. So what was seen is what would expected if the theory was right. And this is a very strong indication that the theory is indeed describing objects, this object within the sky. Another spectacular evidence for black holes, this is what got the Nobel Prize in 2020, last year, is this set of images here. These are the two people, Gens and Getz, who got the Nobel Prize for getting this picture. This is a little movie. It's not in real time. In fact, the movie lasts for 20 years. I mean, I'm not showing it for 20 years. It's compressed in a few seconds, a sequence of images for 20 years, and it's what we see in the center of our galaxy. And you see some stars moving around in the course of 20 years. And this is another picture, the same sort of tracking the movement of the stars. And what you see is that they made very beautiful ellipses, Keplerian ellipses, like they're orbiting around something central, which is a little star. And if you do calculations, a simple calculation, you realize that there should be a single object, which is 4 million times the mass of the sun, to justify these orbits.
Carlo, just a quick interruption. We can't see the movie. The slide didn't move on from the telescope image to the.
Okay, sorry. So you just have to believe me that these stars. I don't. Oh, maybe no. I don't know. I don't know how to do better than this. It's probably going too slowly. The connection for tracking the movie. So what we see, let me just illustrate, what we see is the stars orbiting around a central point and making ellipses. And that's evident that there's a huge mass there whose size we can compute, very, very concentrated. And the only model we have is general relativity black holes. And then there's perhaps the most spectacular evidence, which is another Nobel Prize in 2017. So you see, it's extremely vital black hole physics recently. And this was a detection of the gravitational waves produced by two black holes. So the theory tells us that if you have two black holes orbiting around each other, they emit waves around them in all directions. And so they lose energy. They go faster and faster, nearer and nearer. And so the wave the frequency increases and they're stronger and stronger. So they produce this particular shape that was predicted. And this is a signal that the LIGO observatory detected. This is the signal of the first observation, which reproduced exactly what was predicted. Let me try to see if you can get the, if this works, you get the sound. This is beautiful because the frequency of this signal, it corresponds to a frequency that we could hear in sound waves. So you can translate it in sound waves. And we get this increase in frequency and amplitude, which makes this noise, whoop, very typical. It's called a chirp. So you can hear black holes. Whoop, whoop, okay? So you can see and listen and have a picture, we have recording of this object in the sky. They're extraordinarily compact. If you a black hole of the mass of the Earth will be 1 centimeter in size, 1 centimeter cubic, roughly. So this means that to make a black hole, you have to take the Earth and squeeze all of it in a centimeter cube. They bend the light dramatically. We have seen just this photon ring, the effect of the bending of a light. And we know that there are so many in the sky, that it's a different number of observations of them. In fact, in our galaxies, there are hundreds of thousands, maybe millions of black holes. And there are all sorts, from these huge ones, billions of solar masses, to black holes of the solar mass sizes. They probably are also smaller ones that we haven't seen yet. This is, it's possible. Now, the beauty of the story is that all the observations that I did show you are recent. In the last decades, some last years. But I've studied this object at school when I was a kid in the 70s. So we knew about those, okay? And these are predicted by general relativity. That's a spectacular thing. So general relativity predicts these funny objects. And in my book, when I studied in the 70s, there was all the theory worked out, this Weinberg book. And it said, well, probably they don't exist in the universe because they're too wild. So people didn't really took them seriously as prediction of things real in the universe. And they were wrong. I mean, including Nobel Prize, huge, immense scientists like Steven Weinberg. It took a long time to understand what they were and to digest them. And it's a beautiful story. And these are some of the main characters. So how were they predicted? How do we learn? I would say, just picking up the main characters, there are many involved in that this is the four main people for different reasons. In 1915, Albert Einstein wrote the equation of gravity that changed Newton's theory and is a field theory for gravity. So it's like Maxwell's equation for gravity, is general relativity. And to his great surprise, 1 year later, Karl Schwarzschild sent him a letter with a solution of this equation, which represents the field around a mass. So if the Earth around is a Schwarzschild solution of the Einstein field equation. And if the mass is super concentrated, the Schwarzschild solution has a surface. I mean, the mass is inside, has a surface where funny things happen. The horizon is called. And in the first part of the century, everybody was confused, including Einstein. Einstein was totally confused. He thought that the universe stopped there at the horizon, doesn't continue inside. And there were debate, and people wrote all sorts of things. partly right, partly wrong. The Russians called it a frozen star because nothing seems to move on the horizon. Great amount of clarity came from the work of David Finkelstein, which I think is the first one who really understood that you can cross this horizon, go inside, nothing special happened in the horizon on the surface, and understood the good connection between the inside and the outside, using a good map, good coordinate on space-time that he developed using some early ideas by Eddington. But until the end of the 50s, this was a special solution or two special solutions of Einstein equations. And many people thought that it was just a peculiarity of this funny solution, which is supersymmetric. It's nothing symmetric in nature. And it took Roger Penrose work in the early 60s to show that this is not just a specific symmetric solution. It's just pretty generically, if some mass is sufficiently compressed, something like that is what's going to happen. He proved some theorems. So if general relativity is true, and if something not particularly funny happen, and if you compress mass enough, you get something like this black hole solutions. And Roger got the Nobel Prize in 2020 for this result. So essentially for convincing everybody that black holes are pretty generic in the universe if Einstein theory it's correct. All right. So what is this solution? And let me just go a little bit slowly here because I want to focus on the key aspect of what a black hole is. And I'm using a space-time picture. Some of you are very familiar with space-time pictures, but let me just introduce it. Every point here represents an event, somebody at some time. This is one person, this is another person. And this is the same person later on. And this is the same person later on. So roughly, usually we draw later times upper, and a line here is a set of events at the same time, roughly. But that's going to be the tricky part as well. Now imagine there is a black hole. And this is the center of imagine there is a star. This is the center of the star. The star is here. This is the border of the star. This is near the star, far away from the star, even more far away from the star. Now, if it's a black hole, and this is the border of the black hole, this famous horizon, the funny thing that happens is the following one. And this is what Finkelstein understood. That the more close you go to the horizon, the more your future direction is not up, but toward the inside. Now, for those of you who understand general relativity better, I should have drawn light cones here indicating the future. So instead of an arrow, just think a little cone, the special relativistic light cone, and the light cone bend inside. So the horizon itself is a light surface, which means that if you put some light here, it stays there. So if you put some light on the boundary of this black hole on the horizon, it can stay there. It doesn't move out, okay? And it also means that if you're very near, so you want to fall, and of course you need rockets to stay put, like if you need a rocket to stay some altitude from the Earth. But the more you get close, the more you get powerful rocket. And when you really cross the horizon, no rocket can save you from the fact that your future direction is in. So this is a tricky picture because we want to represent the future up, not on a side. And there is a way of doing that. I just redraw this picture in this way, okay? And now the center of the black hole is in my future, because when I'm inside, my future is the center of the black hole. In fact, I cannot do anything but falling, getting to the center of the black hole. And this is a sort of naive, simple-minded version of the way of drawing space-time, which was introduced by Carter and Penrose himself. It's called the Penrose diagram or the conformal diagrams, in which you represent a path that line can follow always at 45 degrees. So when you're far away, well, the black hole is on the side here. When you're inside, you can only move toward the center. And when you're near the boundary, you can escape if you're outside by running very fast, but you have to sort of push faster and faster. And once you're past the horizon, you cannot escape anymore. Now, I'm going to tell you what happened here at the end of the horizon after. Let's leave it open. What about the inside here? Well, imagine the black hole was formed by a star. In fact, most black holes we see in the sky are well understood as produced by stars that stop burning, and so they're not kept open anymore by the radiation pressure, by the heat, and so they fall into themselves by their weight. So they fall. This is a star. This brown thing is a star. The star falls, and at some point, it enters its own horizon. So it becomes smaller than the horizon. So now the star is inside. This line here is the center of the star. And at some point, it gets incredibly compressed. But then the center of the black hole is not in the future of this point, is on a side of this point, so to say. And if you fall later on, you don't see the star anymore. You go to the center, the star is far away from you. Okay, and in fact, if you think of the shape inside, this is a complication of black holes. This is general relativity. It's the geometry of space and time. It's hard to visualize, but I think we have to visualize if we have to understand what it is. So try to follow me. You're outside and it's just normal space, and then at some point there is a sphere, which is the surface of the black hole, and inside, what is inside? Inside is a very, very long tube. Well, it's not long at the beginning. When the star forms, it's very short. And then as time passes, it's longer and longer and longer and longer. But it also becomes, the tube becomes narrower and narrower. So when you fall in, if you look around yourself, you see you could see one direction, which is very, very long and sort of toward the star, one direction, which is where you come from, the outside, and then around you a sphere of possibility. Here is a circle because I'm missing one dimension. But it's really a long cylinder inside, which as time passes becomes longer and longer and more narrower. So when you cross, you're squeezed in this space, becomes smaller, 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 and then you get to the center, and then general relativity doesn't make any sense. You don't know what happened anymore. So this is what general relativity tells us of these funny things, which are the black holes. So the star that formed it just disappeared somewhere, but there's still this strange shape of space-time. And this extraordinary space-time structure predicted by Einstein's theory predicts exactly everything we see today about black holes from the outside. It gives all the right predictions about black hole. And as I said, let me repeat, at the first, nobody understood it. When it was understood, it was clear that this is a prediction of the theory, but people didn't believe that these things existed in nature. And then they were seen, and now everybody, I think nobody doubts that, let me put it correctly, nobody doubts that those things that we see in the sky, the best explanation we have about them today is exactly the black hole described by general relativity. Now, what about white holes? I promised talking about white holes. Well, white holes also, it took some time to understand them. And now we understand them very well, theoretically, like we understand well black holes theoretically. And also when they were understood, people did not believe that the prediction is credible. And in fact, people still mostly do not think that white hole is credible. If you go in physics department or astronomy department and you ask a scientist, are there black holes? They would say, yeah, I mean, things in the sky are black holes. Are there white holes? No, white holes don't exist. And if you say, well, they're both solution of Einstein equation, you get some arguments for one being real and the other not. But let me tell you what a white hole is. Well, a white hole is just not something where you can only fall in, but something you can only come out. And it's very easy to find the corresponding solution in Einstein theory. You just take the black hole and you reverse the future with the past, and you get a white hole. So it's the same solution with the t switched in minus t. It's a sort of a, take a movie of a black hole, project the movie backward, and that's a white hole. So let me do the picture where the future is always up. It's a picture like this. So there's a center of the white hole from which you can only come out, so to say. And this is the horizon. And then once you're out, you're out. And from you're out, you can only see coming out from the white hole and nothing coming in. And now you see where the difficulty is and why people don't believe that they exist in nature. Because the center of a black hole in the future. So you say, all right, so things fall there. We don't know what happened. Something will happen. But the center of the white hole is in the past. So it's like, where does the thing come from? I mean, there's nothing before. It seems unlikely that something could just whoop, jump out of existence. And that's the reason many people, the intuition of many people is that white hole might not be there. But you know, intuition is tricky in general relativity. And this is the first part of my talk. So all everything so far is thing we see, a theory that is the best theory we have about space and time, theoretical predictions, think we understand very well. And now let's go to what is obviously missing, which is quantum theory. Because we know that we also know that the world is described by quantum theory, and this generativity as we know it disregards quantum theory. So the entire picture I gave disregards quantum physics. Now, what does quantum physics tell us? Quantum physics comes in this story in two ways. As quantum effects of matter that moves in the black hole space-time, and quantum effect of space-time itself, because space-time itself has quantum properties, which are supposed to be described by theory of quantum gravity, which is what I spent my life trying to build. So they're both there. And I'll say something about quantum effects of matter in space-time and about the quantum effect on space-time itself. And the quantum effect of matter, it's a beautiful result that Stephen Hawking obtained in the early 70s, 73, 74. And is that the matter, the classical matter can only fall into the black hole, but quantum matter in some sense can come out. Or more precisely, if you have a black hole, the surface of the black hole actually appears to emit radiation, energy, like a hot body. And as a result, the black hole loses energy, namely loses mass. It becomes smaller, smaller. The technical word that is used, it evaporates. So you leave it there and it evaporates, becomes smaller, 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 smaller. Now, this is there's a lot of discussion of how to think about that. There are many ways of thinking about that in the physical community. I want to tell you one way of thinking about that, which is connected to the quantum theory of gravity on which I'm working, which is the following. The theory of quantum gravity, which I'm working is low quantum gravity, has a main prediction, which is a result of the calculation inside the theory, which is that there are grains of space, there are atoms of space. So space is not continuous, but is made by elementary quanta, little packages of space. Conceptually, this is not too difficult to understand because quantum mechanics, it's characteristic of quantum mechanics to predict that some quantities are not continuous or discrete, right? The light that comes toward me is described by an electromagnetic wave, a continuous electromagnetic wave in the classical theory, but we know from quantum theory that it arrives on me like little photons, one at a time. So there's a granular structure of light. I can think a light of quanta, particles of light, photons. And Einstein's main result with general relativity is that the gravitational field is just the same thing as space-time, the geometry of space. That's a great Einstein discovery. So if the gravitational field is quantum, time is quantum, so the geometry, the size, the shape of space-time is also quantum, and therefore, like light, it must be made by grains. And loop quantum gravity is a mathematics that describes, using standard quantum theoretical methods, these grains, this little quanta of space, which you can imagine as really little quanta, which don't live, the little stones or little blobs or whatever, that don't live in space, they make up space themselves. And the theory says who is connected to who, so they form a graph, and this graph are called spin networks in the language of the theory. And of course, they don't stay there. They move continuously, and space-time is the movement itself of this graph. This is it's an artistic image that was made by a group in Berlin. All this little graph, this little quanta of space forming and being destroyed completely. It tells what the probability for the movement, for the jumping of this quanta of space. Now, if you think that space has this structure, the surface of the black hole, which from the outside is a sphere, is made by little quanta, little piece of something, which have a finite size. And you can imagine it as each of them moving, shaking. And a moving, shaking set of finite things is exactly the way we understood heat, right? A hot air or a hot water, it's a lot of molecules moving. So here we have a lot of quanta of space moving, which implies there's some heat associated to it. And since in quantum mechanics, you cannot stop moving, there is some residual heat associated to it. And because of the specific aspect of gravity, one can sort of see it from a distance. And that's why there is a radiation coming out of it. So that's an intuitive, one way of understanding intuitively Hawking radiation. And let me be clear here. Science is about equations, predictions, mathematics, rigorous definitions. But what matters is the intuition which drives these equations. This equation is not just mathematics on a piece of paper. Tell us about reality. And we have to read this equation in images, and the images drive our dealing with equations. So these images are not just a sort of popular version of something else. This is the driving intuition of many scientists who try to think about these things here. So what happens because of this radiation? I mean, on the surface of this black hole, there is some radiation that comes out and escapes and goes out to infinity. Therefore, the mass decreases. Therefore, the size of the horizon becomes smaller and smaller and smaller and becomes very small at some point. What happened next? And that's the essential question. And that we come at the quantum effect on space-time itself. And where are the quantum effect of space-time itself? They are here when the black hole has become very small. So the surface of the black hole, the horizon, becomes smaller, smaller, smaller. At some point, it's so small that quantum theory cannot be disregarded because quantum theory becomes important for small things. There is a star in the middle, which is becoming more and more compressed. At some point, it's so compressed that quantum theory cannot be disregarded. So here in the center, at the end of the center, if you want, quantum theory is important. Outside, quantum theory is important. And of course, in the middle here, quantum theory is important for the same reason. These long tubes, let me go back, this long tube at some point becomes so small that the geometry of space-time must be quantized. So this blue area here is where quantum gravity comes in. And if you want, the problem of quantum gravity is three different problems. What happened to the star when it gets to super compressed? Technically, we call it a Planck star in the moment in which it's so compressed to get into the quantum regime. What happened if you're here and you get to when the tube becomes very small? And what happened to the horizon when the horizon becomes so small? And this is where loop quantum gravity can help, assuming it's true, because what loop quantum gravity tells us is the transition amplitude, the probability amplitude, the jumps that quantum mechanics allows that classical theory does not allow. So what loop quantum gravity suggests is that you can jump beyond a quantum gravitational region in the same way in which in elementary quantum mechanics you study tunneling. Tunneling is when a particle can jump across a region where the classical equation of motion would tell that it cannot go, but quantum mechanics can go, provided it's small enough. And here is small enough, everything is small here. It's very long, this line. This point is very different from this point, but everything is very narrow here. And so what happens? Here is what can happen. You jump, and a number of calculations using very different techniques, starting from loop quantum gravity, in the last 3 or 4 years have suggested that when you jump the other side, you go back to a classical space-time, but now it's a white hole, not a black hole. And the star in the middle becomes very small and bounces back. And the horizon goes also through a transition, and the black hole horizon becomes a white hole horizon. And the beautiful story here is that apart from this blue region, all the rest is described by classical general relativity. In fact, there's a solution of Einstein equation, which outside is just the outside of a black hole. It connects to the black hole in the way we know the Einstein equation tells us, and it connects to the white hole in the way we know the Einstein equation allows us. Where the Einstein equation are violated is only in this little blue region here. Let me give you some intuition, because as I said, what matters is intuition. This is the outside view. So if you don't view anything, you're just outside, you see the star collapsing on horizon forming, becoming smaller and smaller, something happening, and then a white hole, and then the matter comes out from the white hole. But if you think what you would see inside, this is what you would see inside. So that's a good picture. The star collapses, this long tube forms, the tube becomes more and more long, super long. The star is down there, very, very, very far away. So for stellar black holes, it can go billions and billions of light years inside. The star is at the end of this deep cylinder. At some point, the size of the cylinder becomes so small that quantum mechanics comes in. There is a quantum transition, and you have still the same cylinder, but now time reversed. You know, this is like a bounce. When a ball bounces, then the trajectory is the same, going up at time reversed. So there's a bounce, a time reversal, and then the white hole, this is not coming longer and longer, it becomes shorter and shorter, and everything which is inside come out, and the star itself can come out. So this is a white hole. This is not symmetric in time, because of course, in the first part, there is a Hawking radiation that emits heat. So it starts big, the black hole becomes small. Only when it is small, it can make the transition, be a white hole for a while, and then disappears when the star comes out. So this is the prediction, or a possible prediction, of loop quantum gravity. I mean, if loop quantum gravity is correct, if the calculations are right, if the intuition are right, if we're not missing something, this is what the theory tells us that happened at the end of at the center of a black hole and at the end of a black hole evaporation. Let me just go back. At the end of the Hawking evaporation, the black hole becomes a white hole. And if you fall inside, you cross the quantum region and you come out the other side. Just one detail, how am I with time? Just one detail. This process is very long because stellar black holes take very long to evaporate. So this process, you should think for a stellar black hole, it's an order of billions of years seen from the outside. But if you go inside, you go very fast to the center and you go very fast out. For a stellar black hole is milliseconds to go to the center, so milliseconds to go out, and then you come out. So you can view this black hole to white out like a shortcut to the future. Inside is a millisecond, outside is billions of years. And quantum classical generativity permits that. That's exactly what classical generativity permits, right? Clocks go at different speed. We know on Earth, we've measured that. If you go a little bit closer to the Earth, there's less time. On Earth, it's just a teeny effect, 1 part in 10 to the 16. But in a black hole, it's a huge effect. So a billion years outside, it's a millisecond inside. Inside is huge compression, super rapid falling, expansion, but it's immensely redshifted, slow down. You see this in slow motion from the outside. So what would be a black hole? It's a slow motion of a star collapsing to a quantum region and bouncing, quantum bouncing and re-expanding. All right, so this is a possible scenario. Am I sure it's true? No, of course. But I personally find this the most convincing scenario of what is happening inside and at the end of the life of a black hole, with respect to other alternative, which I see discussed. Can we prove it? Well, we should see some effect of it. And that's just one last slide. I just want to mention some possibilities because there's work, the paper's been written, but we're in the realm of speculation and attempts. But once again, the spirit in which I do that is, remember very well that when I was at the university, the possibility of observing black holes was considered so remote that certainly in my life, I would have no chance of seeing one. And now I see many. So perhaps we will be able to see white holes produced by a quantum transition from black holes. The actual black holes we see in the sky will evaporate and make this transition, but too much in the future for us to see. So if there's a chance to see one, they should be very old black holes and small. So if they're small, the lifetime is shorter. And it's very possible that in the primordial universe, black holes formed because of the great heat and compression at the time, or even earlier, if the Big Bang was a big bounce, which is predicted by a number of theories, including loop quantum gravity. So in previous phases of the universe, there could have been formed small black holes that went through the bounce and are still there. Or in the primordial universe, there could have been small black holes formed there. So these might have evaporated, bounced into white holes, and they could be around. And what could they be? Well, they could be very small things, micrograms, a powder, which interacts only gravitationally, because that's what black holes are. And dark matter is exactly small things which interact only gravitationally. So perhaps we've already seen all these white holes, this dark matter, or at least a component of dark matter. Could some observational dark matter could be sharpened to sustain this hypothesis? Work is in progress. For the moment, there is nothing. There are possible objections to this scenario. There are possible answers to this objection. There's big discussion about that. Alternatively, from the white hole, things come out. And if the black holes formed in the very early universe, it was very hot there. So there will be very hot photons there. So the hot photon there is trapped into the black hole. A millisecond later comes out in our universe. I mean, much later. The universe is always the same, but much later nowadays. And we could see it. And this could be some of the super high energy cosmic rays that we see. So we might see cosmic rays that have that, that origin. There might be peculiarity of the spectrum, their relation to distance, some aspect of the observation that might perhaps indicate that, that they are in fact coming out from white holes formed in the primordial universe. I'm not going into all these details. It's astrophysical details. They're fascinating. They're beautiful, but it's all being discussed. I just wanted to give you the overall picture. So for the moment, the situation is that we have a theoretical scenario and some very tentative predictions and a discussion about possible phenomenology of all that. So that's my last slide. To summarize, I think it's an extraordinarily beautiful story. which I had the good fortune of, witnessing during my life. I studied general relativity, I remember, in my class in Bologna, which were this funny, so only theoretical things that nobody believed were true. And during my life, I saw them actually being found in the sky. They were extraordinary prediction. Space and time become so incredibly distorted to be, in some sense, hard to imagine how they stay together, but nevertheless, with a little bit of mathematical exercise, perfectly possible rationally to understand them. And all predictions beautifully verified in gravitational waves, in images, in observational motion of stars and else. That is a success story. Is not the end of the story, because there's quantum mechanics. White holes might be predicted as being produced, a quantum mechanical phenomenon at the end of the black hole evaporation. I hope, so that before dying, to see the first hints that this is a true scenario. Nature has also implemented this. Nature could have done that. Why shouldn't have she done so? Thank you.
Excellent. Thank you very much, Carlo. I think we need all a minute of cool down time and sorting the thoughts before we move on. So let's take a 120-second break to look at the Q&A. And I encourage the audience to please put their questions into the Q&A windows, and we will begin sorting them. Okay, so again, thanks so much for this great overview. So let's start the Q&A with Adriano. Adriano, you had a question.
Yeah, so thank you again, Carlos. It's been a wonderful talk. I've seen many people asking you to confirm that in this universe, there has been already time enough to form these white holes and see them some way. So we don't have to wait for the, 10 to the 10 giga years or something for a black hole to evaporate first.
Yeah, so it's a possibility, it's something we don't know. So the black holes that we see in the sky are definitely going to evaporate too much in the future for us to see. So the possibility of having black holes for which we could see the effect of the transition to white hole depend on the fact that there are small black holes in the primordial universe. And this is something which theoretically is possible. And there's a lot of attempt to model the formation of black holes in the early universe. But there's no strong evidence that they exist. So it's a possibility, it's not a certainty. And as I said, it's a double possibility. They could have been formed in the early universe. Intuitively, it's clear. It's very hot, very compressed, a large number of fluctuations. Fluctuations can fall into its own horizon. Or it could, if there was a big bounce, so if there was a phase preliminary to the Big Bang, they could have gone through. So this is it's an even more speculative possibility because we don't know if there was a big bounce. So the answer is yes, it's possible.
Thank you.
Okay, Max, you're next.
Max, go ahead. Max, you're muted.
Sorry. Yeah, I didn't see it. Thank you very much for the talk, Carlo. It was very interesting.
Thank you.
I have the idea of quantum gravity. People expect the quantum gravity to solve the problem of the singularity of the, in general, singularities in the classical solution. So my question is, to what extent your calculation of this tunnel effect from the black hole to the white hole needs the singularity at all? Whether it has to be there, the singularity for this transition to happen, or it could be a solution to that particular problem. I mean, in principle, the whole motivation of quantum gravity was to get rid of the singularity, not to use it. So I'm not, because I haven't seen the calculation, I'm not sure to what extent you actually need the singularity for this process to happen.
I'm glad you raised this. This is a key point. I should have perhaps discussed better. It's a complete solution to this particular singularity. I don't want to say all possible singularities that appear in general relativity. The problem of singularities is the following. There are some regions, when you take the solution of Einstein equation, there are some regions in which a singularity develop. And one of the typical feature of singularity in this case is very clear, is that the curvature becomes infinite. Some curvature scalar become infinite. Now, if you think in quantum gravitational terms, you expect, if you think in quantum mechanical terms, you expect on dimensional grounds that quantum mechanics becomes relevant when the curvature becomes Planckian. So classical general relativity just doesn't apply when the curvature is too high, because you expect it to be corrected by quantum effect. So I think from a mathematical point of view, singularity is a clear thing in GR, but from the physical point of view, there's no singularity. It's just, we know that before getting to the singularity, something else come in. So what happened in loop quantum gravity? Well, it's pretty simple. When you get to this region, you don't have to use the Einstein equation. You have to use transition amplitudes, the quantum transition amplitudes, and these remain well defined. So you can compute the probability amplitude for going from one geometry to another geometry. And you do that, the calculation that we do is a transition amplitude. So given an initial geometry, what's the probability of getting to this other geometry? It's like tunneling, right? I mean, your particle arrive, what's the probability to finding the other side? It's a bit different because in tunneling, you can bounce back also. You have transmission and reflection. Here, in a sense, it's tunneling with only transmission. So it's not exactly the same, but it's very similar to tunneling. It's going over a forbidden region in the Einstein equation. Or if you want, if you think in terms of path integral, you're not anymore dominated by the classical trajectory because there isn't any classical trajectory, but you're just integrating over a different path. So another way of viewing it is that you go away from a classical state because space-time geometry is in a quantum superposition for a while, but then you can go back to the, so yes, it's exactly a solution of the problem of singularity in GR. And intuitively, it's because the quanta have finite size. So once you reproduce the Einstein equation in terms of finite quanta, as long as you have big wavelengths with respect to the Planck size, you can, but when things are too small, the Einstein equation are not good enough, and there is no infinity. That's the key point. There's nothing arbitrarily small in loop quantum gravity. There's a bottom line to divisibility of space.
Okay, thank you.
Marek, let's go next.
Yes. Well, actually, following this
Marek,
question,
sorry for having simplified dramatically the Einstein Penrose diagram.
No, it's fine.
In your eyes, I was thinking, oh, Marek is putting his hands in his head. Carlo is simplifying too much.
It's fine. Actually, following this last question and question asked by Manuel David Morales, I would be grateful for your answer to the following and your intuition comments on the following problem. You see, now we are observing two black holes merging. From your point of view, from your description, the center is some regular space. There is no singularity inside. This whole process of merging is really dynamical. We don't know how to describe it, but definitely very strange things are happening inside, merging also these two quotation marks singular regions. Do you think that can we hope on some way of seeing outside from the space what's going on inside, in a sense, sneaking into the interior of the merging black holes by looking at what's escaping.
Ah.
This ring down phase.
Yes, I see very well the question, and I wish I could give you a, a good answer. I can give you a tentative optimistic answer, but at the same time, a very ignorant, a very declaration of ignorance. And let me start from the negative. I have no intuition of what happens when the two black holes come together. I would expect that it's possible to make a story there, somehow to replace the singularity with a smoothing out bounds of the geometry where it never somehow the tube becomes small and then start growing again, but in a way which is consistent with two of them happening and making one. I don't see one. It's definitely something which is in our research program. But this comes a pessimistic part. I don't have a clear, I talked about Schwarzschild, right? Yes. My picture, I don't have a clear picture of Kerr.
Yes.
Bounce. So
yeah, I know. The
okay.
Inside
so it's not just the complicated thing of two, it's just one rotating one. I can write the full bouncing metric, the effective metric going through the violation of Einstein equations nicely, beautifully. Some students do that with great care for Schwarzschild. The problem, okay, now you do it for Kerr, hasn't been solved yet. So here we are.
Okay, thank you.
Yeah, that would have been actually my question. What about the angular momentum content of this bounce? And are there any effects of the simple Kerr reversal, right?
Yeah, okay, yeah, a good question, Thomas, of course. I mean, obviously, we expect that angular momentum is conserved from the outside. So you go in and a spinning black holes like that, you come out to a white hole spinning in the same direction, obviously. I mean, because of angular momentum is that. So, but once you try, at this level, we have an intuition. But once you try to write the actual geometry inside, you see, one of the problems is that the structure, the causal structure of Kerr inside is complicated. It's horrendously complicated, and it's very unstable. So there might be, in reality, all things considered, Schwarzschild might be more realistic than Kerr in a sense, because once you perturb a little bit Kerr, you have this formation of other singularities.
Yeah, I mean, you have this ring singularity forming, right? At some
yeah.
point. So how do you treat that in this loopy picture that you brought here?
These are exactly the technical, the steps that theoretically have to be done to clarify what goes on. So the initial models were super simple, and we're trying to do. I mean, intuitively, something should happen. I mean, it's if you think, you see, in the Schwarzschild case, what the theory is telling us is that it is just like a repulsion that prevents that stop curvature from growing too much. So imagine you add to Einstein equation a term that says when with a Planck scale, when curvature becomes Planckian, it just cannot grow much and it comes down. What would happen? Now it's not hard. It's very hard to figure out what would happen in Kerr. It's very easy to see what happened in Schwarzschild. In fact, in Schwarzschild, it was already, the intuition is already there. There's a paper by Singer, much like you might know it, in which it just glues a Kruskal spacetime with another Kruskal spacetime, and it shows that they glue incredibly well. And in fact, you can even smooth the geometry in between and have a perfectly nice Lorentzian geometry in which the tube becomes to a finite size and then opens up. It's beautiful. It's just, so so the intuition is good. I mean, somehow there, but doing the same with care, I've not yet been able to.
Well, but Carlo, you have to realize that the black holes which exist in our universe, this real
care and not
all probably care.
Of course, yeah. Of course, yeah.
I think remember there was a paper last year by two Russians that actually speculated that all these ring galaxies are exactly those reversed Kerr white holes that have been tuning the gravitational field around those galaxies to make them appear as such. Well, what do you think about that?
I am not an astrophysicist, so I don't want to. They are competent on that. But my reaction when it started to become obvious that there is a very large black hole at the center of so many galaxies, or almost all, not all, which makes things more complicated, but most of all, my immediate reaction was, well, it's not the galaxy that has a black hole in the center, it's a black hole that has a galaxy around it. I mean, it's just, there's this huge thing in the center. I mean, the huge thing is still small compared to the size of the galaxy. It's not dominating it in terms of mass, but nevertheless, it's so dominating it in terms of in a qualitative way that one wants. So my instinct is that should be something should be right in that direction. But I don't think it's the astrophysicists have yet clarified the story of these big black holes. I know the science is moving fast in that direction, so I may not be up to date.
Okay, so let's go to Reza next.
Thank you for your talk and intuition invoking illustrations. So is my gathering from your talk correct that a white hole is the destiny of every black hole? So are you predicting every black hole? Does your calculation also apply to supermassive black holes and micro black holes?
Yeah, so the calculation applies for all masses, but it's relevant only when they have evaporated quite a bit. So the ones we see in the sky are just not doing that yet, unless you go in. But that's not what we see. Remarkably, a small black hole, this is something which I believe a lot of people is confused about. A small black hole young and a small black hole old, they are very different. One has a little tube inside, the other has a huge tube inside. So this idea that a black hole, it's only determined by mass and angular momentum. Yeah, from the outside. But not what is inside. But so at the end of the day, they all become small. The throat becomes all small, assuming that Hawking is right. But this seemed to be, we see no reason he should have been wrong on that. And then this applies. So in fact, I think that it would apply for all sorts of black holes. I expect this applies even where I'm not able to do the calculations. And in loop quantum gravity, there are general arguments that you never have a singularity because there are general arguments that says that you always avoid singularities, essentially because everything is finite in the ultraviolet.
Max, you have another question?
Okay. Thank you. I have another question. So you emphasize that this calculation is a quantum probability amplitude from going from one state to the other state. So I have a kind of historical question. How did you get to that result? In quantum mechanics, you put the initial state, the final state, and then you compute the amplitude to going from one to the other. So my question is, you had the idea, and then you calculate and then found a non-zero probability, or you were making some calculation and realized that, oh, this process might occur. The point I'm trying to raise is whether this is a prediction, or whether from the theory, or whether you consider two possible states and they have proved that there's a non-zero probability from going to one to the other. what the bottom line really is the normalization of probabilities, because in quantum field theory, we know that there are infinities and there are many issues related to the absolute value of this calculation. So there might be a non-zero probability, but it might be very, very small. So how do you normalize the probability in case that, well, I think that's the question. I don't want to extend it further.
Yes, yes, this is one of the questions on which we have agonized most in putting all these things up. Let me try to, do you see the image here? Let me try to in quantum mechanics, when you compute probabilities, you have probabilities with respect among alternatives. So if you have the probability of an atom decaying and a Geiger counter clicking, you have probability with respect to clicking another time, with respect to not clicking, with respect to another one clicking. I mean, this is a probability by itself is not. And here is quantum gravity. So all these things are tricky, and you have to rethink. In this particular application, the way to think about is to realize a previous result. So we face that on we address that on a previous result. The previous result is that there is a solution of Einstein equation, which is exact and classical, which goes all around here. And that was a total surprise for us. In fact, was a shock, because if you think for a moment, of course you have a solution of Einstein equation with an external black hole and a white hole, but the white hole is before and the black hole is after. So how can you switch the two here? And the point is that this is locally isometric to the Kruskal solution, but not globally. So you really can get this by taking Kruskal, cutting and pasting, and bringing back together. And if I had some time, I mean, it takes some imagination how to do that, but you have to take Kruskal and take one part like that and one part that fold over, cut it open, and you can do that. So there is an Einstein solution all around here, which of course depend on parameters, because you're cutting something, so you're free to adjusting stuff. So the external Einstein solution depends on a number of parameters. And now you say, all right, so here, of course, the Einstein equation are violated because there is quantum mechanics, and I have some initial state and final state which depend on these parameters. So now you can write the amplitude as a function of these parameters, and ask the probability of this happening or that happening given this parameter or this other parameter, okay? I mean, can this happen before when the mass is larger? So when it hasn't evaporated more, or it has to wait for the last minute, and other things like that. Now you can say, wait a minute, you are cutting out just a region of space. How do you know that, and this is a normalization question, how do you know that something else could happen and you are forgetting, you're normalizing wrong here? And the answer is, I don't know. I mean, we don't know. We don't. So in a sense, I'm not saying I have a solid quantum theory that gives the prediction that this is going to happen given the initial condition. I'm saying this is a possible process allowed by the theory that I have, which in this range of parameters seems to be probable. So it seems to be happening when this is sufficiently small. If somebody in principle come and say, look, your same theory could predict something else which is more probable, this might happen, but I don't have a control of that.
Thank you.
Okay, let's just pass to some questions from the Q&A. So there is a question from Gustavo Melgarejo. He says, white holes are produced only for quantum effects, or is it possible that the modified theory or gravity produces white holes in a classical matter?
I think that, as far as I know, this is the only way you can think a white hole is produced. because if a white hole is characterized, I mean, depending what we mean by white hole, if it's characterized by the initial singularity, you have the old question. I mean, how classical you can come out from initial singularity. So now I don't know with alternative theories of general relativity, but I'm not aware of any alternative theory in which you can classically produce a white hole.
Okay, there's another one from Odilio Aguiar. He says, could white holes also emit gravitational waves? Do they have quasi-normal modes?
Yeah, they could, and of course, they're. I mean, from the moment in which you're outside the quantum region, you're back to general relativity. So we're completely within the equations that we know. I mean, they're complicated equations, but we know. So, and in fact, they could shake, they could emit things. It's not totally obvious, the physical white hole, because there's a characteristic instability of white hole. But they could, definitely it's possible that energy which is inside can come out. And if there is non-symmetric configuration of the gravitational field, is going to radiate out and do gravitational wave.
Can I follow up?
But these are small, right? So I don't expect to see merging of white holes, because these are very small things.
Okay, let's push this to the extreme. What about merging on white and black hole?
I have no idea. I have no idea. Okay.
That's a great research project.
Yeah. I have no idea. I'll have to think about that. I'll ask my students to come out with or my collaborators.
Okay. Paula?
Yes, there's another one from Veronica Vasquez. She asked, can the jump from black hole to white hole produce gravitational waves in some manner?
Yes, we are very much intrigued by the what happened at the tip here, this process here. And in fact, I wish this could be understand better. One of the things we're trying to do is to come up with a numerical, because we have the equations. The loop quantum gravity gives us these transition amplitudes, but of course they are complicated again. So we're using a numerical analysis for describing what happens here. And I don't know what's gonna come out.
Okay, Reza, you had a question from the Q&A, I think.
Yes, I have a question from Q&A. Brian Ortigoza has asked, at the beginning of your talk, you did mention about the information paradox. Can you touch about that? Does this solve the information paradox?
Yes, yes. It's a bit of a long story. Let me try to make it short. There is a naive version of the information paradox, and there is a sophisticated version of the information paradox. The naive one is that the information that falls into the black hole is lost forever, so it's strange that we lose information. And this is because if people think that at the end of the evaporation, whatever is inside disappears, then there is a problem. Information is lost. And people think quantum mechanics is impossible to lose information. And then there was a debate. Quantum people says, no, you always have information preserved because of unitarity. And some relativists say information is lost and so on. But all this disappears if all this becomes irrelevant if the things that fall in come out, okay? Or said it more technically. And that's why at the beginning I said, be very careful what we mean about a black hole. The horizon here, the horizon of black hole is not an event horizon. It's a trapping horizon for those who are technically, which means the horizon ends at some point. It doesn't continue all the way to infinity. The event horizon continues all the way to infinity. So in many books, a black hole is defined as the existence of an event horizon. In fact, Hawking wrote a paper one day saying black holes don't exist, which was a provocation, like in typical Hawking style. What did he mean? He simply meant if we define black holes as event horizon, careful, because quantum mechanics tell you that the horizon becomes small and then disappears. So therefore it's not an event horizon, because event horizon goes all the way to infinity. Still an horizon, it's just a different kind of horizon. It's called a trapping horizon. There's no event horizon. The information that comes in just come out. This is a total solution of naive question, naive version of the paradox. But there's a more sophisticated version of the paradox, which is the following. When the black hole is very small, imagine here the surface, the area of its horizon is very small. People say, and that's, you find it all over current literature. If it is very small, the area of the surface is very small. It has low entropy. It can have only a small number of states. And therefore, there cannot be information inside enough to sort of contain all the information that has fell in. And because of that, a lot of people, especially coming from the string world, got convinced themselves that the information have to come out before the quantum region. And so that the early Hawking information and the late Hawking, the early Hawking radiation and the late Hawking radiation must be correlated. And in the late Hawking radiation, there is information about the early one. And this is the origin of the firewall paradox, of the scrambling, of the EPR, of a lot of attempts to solve the paradox. I think that this is a mistake. The mistake is to take too seriously, to overplay holography. It's not true that if the surface of the black hole is very small, there's no way of having information inside. Of course it's true, because of course there's information inside, because the volume is enormous inside. When the black hole is very small, an old black hole, which is almost completely evaporated, it's very teeny, but inside is huge. It's that you can take all the information that you want. So the people who overplay holography and say, oh, it's small, has a small number of degrees of freedom, they're confusing the degree of freedom that one can see from outside from the degrees of freedom inside. So I think that they're trying to solve a paradox which is not there. It's due to the overbelief in holography. Holography is true in some sense, but if you overplay it, and people doing ADF CFT have made it as a dogma that all the degrees of freedom you see from infinity, and I think they get confused here. That's my take. So brief answer, I think that the information paradox is completely solved by this picture. If this picture is correct, there's no information paradox. Sorry if I was a bit technical here, but I wanted to give a precise.
Adriano, did you have a question from the Q&A?
Yes, I've seen a couple of people asking about the possibility to directly observe these white holes. So do you have any estimate about their potential luminosity? What do they emit, particles or also photons? Let's say, imagine you have a black hole, a primordial black hole of the right mass to become a white hole now. What would we see at this point?
There are a number of papers exploring that. I just mentioned very, very fast at the end of the talk. And we're changing our mind. I've been changing our mind. At some point, I got very excited because I was hoping that the quantum transition were telling me that this transition could happen when the black hole is pretty large, still pretty large. And then we had an estimate of that this could be very visible. The transition itself could be very visible. In fact, at some point, I was excited that it could emit in the radio and be connected to the fast radio burst. Now, I mean, there are more convincing stories about fast radio bursts, so I don't know, but it seems a little bit more likely to it. The gamma rays that come out have a very peculiar frequency distance dependence that could imprint in their distribution. So that could turn out to be a sort of smoking gun to distinguish the radio, the gamma rays of high energy emitted in this way from others. It's complicated because the overall, the question was about the luminosity and how many of these, it depends on how many black holes are formed in the early universe. So it depends on the full cosmological model. It's a complicated thing. There are people who work on that. I try to follow. I'm not a cosmologist, so I trust them. I'm more working on the theoretical models of what could happen. My hope is that, you know, various people working on from different sides, at some point this would clarify a little bit. My real hope is that there could be evidence that this is dark matter. So every time there is a dark matter candidate that does not work, I'm happy. Because, you know, for a moment, everybody thought it was a supersymmetric particles. Now it's just very few people consider that a reliable possibility, less and less. So if it is nothing else, they could be small white holes. But this is not a strong argument.
Excellent. Thank you so much, Carlo, for this very, very fascinating talk. And the field is absolutely amazing and mind-blowing. So there is lots food for thought. We have tons of questions still in the Q&A that we will post probably later at the video in the description that we will publish on YouTube. So thank you again for taking the time to tell us all about black holes and how they form and evolve and then turn into white holes. Thank you so much, panelists, for being with us today. And thank you, audience, for sticking with us. So please be so kind and fill out again the survey at the end of this talk. Our next scheduled Golden Webinar will be on February 5th and will be given by Martin Rees on progress and frustration in cosmology. So that's going to be an exciting one as well. Until then, stay safe, stay healthy. Until the next Golden Webinar in astrophysics. Bye, everyone.
Gracias. Thank you very much.